video we'll have a look at the problem named minimum meeting rooms, which is classified as a hard problem, and we'll have a look at how we can go about solving it. So essentially, we have been given a list of intervals representing the start and the end, the time of the end meetings. We have to find the minimum number of rooms required to hold all the meetings. We do have a few examples here which go through what it would mean to identify the minimum rooms. So for example, if we have a list of meetings here, we need 2 rooms to efficiently do or hold these meetings. Since we have an overlap between 1 and 4 to 5 and 7, 9 can occur in any of the 2 rooms later. Here we need 1 rooms as there are no overlaps between any of the meetings. 1 room should be sufficient. In this example, we need 2 rooms because 1 and 4 overlaps with the other 2 meetings. So we need to have at least 2 rooms to be able to hold all the meetings. And similarly, we have an example here. We have a visual description of how that would look. So for example, if we spatially represent it, and this is the key here, actually the reason that they provide an example representing it spatial is already an indication that we will have to sort all the meetings on the start of all the meetings. So here we see that in this example, 2, 3, and 3, 5 would need 1 room as they are not overlapping, and 2, 4, and 4, 5 would need an independent room. So essentially we need 2 rooms. So one thing which I wanted to discuss here and provide a quick overview of was, I mean, in try it yourself solution, they already go ahead and import all the functions from the heap. Then this becomes an indication as to how you want to approach this problem. And quickly, like, one of the approaches which you can actually take is using the min heap. And just to give a quick overview of what min heap means. So a min heap would represent a complete binary tree, but the essential aspect which we want to focus on here is that the root of this tree is basically the minimum of that set of numbers if you were to represent it as an array, for example. So like how would we go about using this idea in our implementation here? So essentially what we want to do at this point is, say, as we are iterating through all the meetings, and we have a min heap where we have the ability to query, say, the minimum end time within that heap. So for example, if I'm going through this list, let's imagine it is sorted at this moment. So the first element in that sorted list will be this 2, 3. And like as the first step, I would push this element, say, into the heap. And the minimum at this point, or the minimum end at this point, will be 3. And as soon as I move to the next meeting in this list, which is this one, so I will see if, say, the start of this meeting is more than the end of this, say, the minimum meeting. If it isn't the case, I would need a separate room in order to have this meeting. So which isn't the case in both these scenarios. So I'll push this element into the heap itself. And now the length of my heap will be 2, essentially. So I would need 2 separate rooms at any temporally aligned occasion. And for example, if I have these 2 elements in the heap, and I say move to the next meeting, which is 3, 5, sorted on the start, and I see that the start of this meeting is greater than or equal to say this meeting here, it would, or I mean, end of this meeting here, it would essentially mean that I can host this meeting in the same room as the one where this meeting happened. So I would not need a new room anymore. So essentially at this point, what I can do is I can push this or pop this meeting out of the heap, and I'll only retain these two meetings as they're happening in separate rooms. So once I have these meetings, say, in the heap, I go to the next meeting, and I see that the start of this meeting is actually greater than or equal to the end of the minimum element in the heap. That would mean that I can host this meeting in the same room where this meeting is happening, and I can push or pop this meeting out of the heap, and essentially I will end up needing 2 rooms at most, or 2 rooms in order to go ahead and host this meeting at minimum, actually. So I hope this goes ahead to provide an intuition around Min Heap. And let's quickly have a look at one such implementation and how it would look like. So like the first thing which we need to do is we want to sort all the meetings. Okay. I will just reload it once to see that all the code is actually present, because I remember there was a larger than implementation in the class, but it's missing at the moment. Okay, anyways, let's try to go ahead with a simpler implementation. So the first step would be to sort the meetings, and we know the drill. We want to sort it based on the start element. We see that the meeting is a class and we have a start attribute there. So we simply go ahead and sort it on that one. We would want a min heap, and we want min rooms, which will be 0. And as we saw, we want to iterate through all the meetings, and at any point in time when we look at a meeting, we want to look at the heap and say, okay, first we want to say that the heap is not empty, otherwise this comparison would not make sense. And at the same time, we also want to make sure that another condition would be to make sure that the meeting.start is more than or equals to min heap 0.end. So essentially at this point we are taking the root of that heap which we had a look at quickly here, and specifically looking at the end element. If the start of this meeting is more than or equal to this element, it would mean that we can host it in the same room. So essentially, in order to effectively keep a track of the number of rooms we need, we want to do a heap pop, and we want to remove this element from the heap. So essentially, at this point, we want to remove the root. Okay, this sounds good. So we have been able to remove it, and at this point, if this condition hasn't been met, then we essentially push the meeting into the heap, and our min rooms would basically be the maximum min rooms and length of the min heap. And this is what we essentially want to return. So the implementation overall is quite simple. I'm just trying to see in case we're missing anything specifically here. Let's separate it out. Yeah, okay, let's do the dry run as we had in the previous case. We go through each meeting. This one we draw the comparison. Right now it's empty, so this comparison would not hold. Then we'll move into this meeting. We'll simply go ahead and push this into the heap. We'll go into the next meeting. Again, this comparison would not hold, so we'll simply push it into the heap. Then we'll move into this meeting, and this comparison would hold with the first one. We will drop the first element from the heap, and we will push 3, 5. And at the end here, we just simply want to take it out. So I think the implementation is fine. Let's have a run and see if it's in line with what we are expecting. So essentially at this point we have had to provide the min heap here, but as we run it we see that the less than operation has not implemented, but I saw it implemented somehow in refresh. It actually went away. So let's quickly go ahead and implement the less than function as well. So basically the operators which you see less than say on objects, you can go ahead and define these functions here. So essentially what we want to do is we want to return self.end is less than other.end, and this essentially means that we are comparing this object with another object, and we want to return true if the ends of these objects, so the end of the object I'm interested in is less than the other object itself. I hope that explanation was clear, but again, feel free to reach out in case it was not. And how many instances did we have? We have 2, 2, 1, 2, 2. Let's look above and see if this is in line with what we... Okay, I think we have an additional example here. So let's take a look at this example. Here we saw with the number of rooms we needed were 2. Here, do we have an overlap? Yes, we have an overlap with both. Hence, we'll need 2 rooms, and we do not have an overlap between these. Let's have a look here. Do we have an overlap here? 2, 4, 6, 7. No, we do not have an overlap, so we only need a single room. In this example, we have 1, 4, 2, 5. We do have an overlap here, and we don't have an overlap here, so we need 2 rooms again. And the first instance, again, we need 2 rooms. So it seems like the implementation is working fine. At this point, I'll be more interested in looking at the runtime of the implementation. So we know that the sort operation is n log n, and in this case we are only going through all the meetings once, so this will be an O of n operation. But what I'm interested in knowing is how expensive are these operations here. So let's have a look at the solution and what is the final runtime here. So the time complexity for sorting is n log n. This is due to the sorting. Each of these operations can take. Also, while iterating the meetings, we might need to poll offer meeting to the priority queue. Each of these operations can take log n. Okay. So each of these operations is log n when it comes to our Min Heap implementation. Overall, our algorithm will be n log n. Okay, so the time complexity of this algorithm is n log n. And the space complexity again is O of n because of the sorting. Insert all the meetings into the Min Heap, which will also take O of n. Okay, so the space requirements are primarily from the sorting and the Min Heap. So essentially the worst case scenario both can be O of 2n. And as we know, big O, it'll be essentially n. So I hope you found the explanation clear enough. Please feel free to reach out if there are any questions. Until the next video, have a great day.